Hello everyone, my name is Hargyo. I'm currently a PhD student at the School of Computer Science, University of Birmingham, UK. I'm working under the supervision of Dr. Rami Bahsoon, and I'm very grateful for this opportunity to present our research on a conceptual reference model for human as a service provider in cyber-physical systems. Cyber-physical system is one of the enabling technologies for Industry 4.0, along with AI, cloud, and big data. CPS often involves human on their implementation. One good example is smart manufacturing. Smart manufacturing is harnessing flexibility from human-machine collaboration to allow manufacturers to adapt more easily to shifting demands in products and processes. Human and machine can help each other during the adaptation. Fully automated CPS can excel in strength, precision, and speed, and humans with cognitive abilities, consciousness, and skills can adapt more quickly to new requirements and tasks. They can learn from each other. In many common CPS use cases, humans, when kept in the loop, are generally an operator. The users who instruct or initiate requests and receive service from CPS. So in this sense, humans are service consumers. However, many complex CPS is essentially a combination of computers, machines, and people who work together to achieve system goals. In such systems, humans can provide services by performing tasks based on their ability to sense, act, store, and process. Therefore, human in the loop can be viewed as not only the service consumers, but also as the service provider. Several works have proposed service model and service composition for CPS. However, these studies do not pay much attention to human as a service provider in CPS. Human characteristics are not explicitly modeled. Humans are mostly considered part of the physical entities, along with robots, vehicles, sensors, and other actuators. The contributions of this research are as follows. First, we define the problem of human as a service in CPS service composition as part of the everything as a service paradigm. Then, we contribute to a novel reference service-oriented architecture ontology model for the CPS environment that considers human characteristics and their dynamics. So our proposed ontology model is an enabler and prerequisite for engineering a self-adaptive CPS. We present a pragmatic shift towards acknowledging that both human and machine work in collaboration as service providers. Our work is under the umbrella of everything as a service. So everything as a service is a concept for service and applications that user can access over the network. Human-in-the-loop cyber-physical systems basically integrates computations, networking, and physical processes that involve human in the loops. And these components come with different capability. Humans can be accessed and interacted with this system through handheld devices or other human interface devices nearby. We define human as a service in CPS as a service with human capabilities and properties. These are human as a service providers that can work either in isolation or in collaboration with machines in CPS. They can work together to sense, do the computation, actuate, learn, and or transfer its learning with the objective of providing more socio-dependable and human-centric service composition model for CPS. We classify human service in CPS into 4 categories as follows. The first, sensor service. Humans provide the service actively by reporting an event or phenomenon detected by the 5 senses, or passively by allowing their activity or behavior to be recorded to see social phenomena. Second, processing service, by using human cognitive abilities and knowledge to make decisions. Third, actuating service, by performing physical or corrective action, specialized actuation from human to fix problems. And the last one is adaptation service. This service is basically a composite of the 3 services above, where human can act as an adaptation promoter for other nodes. We argue that understanding the classification and relationship between the attributes of workers and their jobs is essential to build an adequate human as a service model and prerequisite for developing a self-adaptive model. We have studied several existing frameworks and decided to use ONET as it is considered to be the primary reference for other occupational frameworks and models. So in ONET framework, every single job requires a different selection of knowledge, skills, and abilities, and performs a variety of tasks and activities. These particular characteristics of an occupation are described by the content model as shown in this figure, which reflect the characters of occupations through job-oriented descriptors and people via worker-oriented descriptors. Worker-oriented descriptors consist of several attributes. First, worker characteristics are defined as enduring features that can affect both performance and the capacity to learn knowledge and skills necessary for the efficient performance of the job. We have abilities, occupational interests, work values, and work styles under this attribute. Second, work requirements, which reflect an individual's developed or acquired qualities that may be correlated with work performance. This attribute consists of skills, knowledge, and education. The third, worker experience, which is previous work experiences that involve employee experiential background such as certification, licensing, and training. To create a self-adaptive human-machine service provisioning, we need to have a model that includes both human and machine capabilities. To simplify semantic discovery and reasoning, we propose an SOA model for human-in-the-loop CPS, which is expressed as ontology. We call this as SOA HITL CPS ontology model. We use ONET as primary reference to build human service capability model. This figure is a top ontology of our proposed ontology model, which explains that humans and machines are within an organization where each node has its function and task, which generally correspond to context, and also capability to accomplish the task. Each node can be a service provider or service consumer. To make it more interoperable, we propose a service model following the OWLS, which consists of three main parts, namely service profile, process model, and service grounding. Service profile allows providers to advertise their services and also requesters to specify the service capabilities they require. This figure is our proposed human capability model. Humans basically provide service in every task they do within the scope of their job or profession. Therefore, as mentioned before, we use ONET occupation framework to build this human capability model. Human characteristic represents psychophysiological factors that distinguish human and affect the service provided. It is defined by preference, ability, and performance factors. Qualification are attributes that describe a person's appropriateness or fitness, achievement, and quality, which can be either skill set, knowledge, formal education, or experience. Potential is latent human capacity to improve for growth and development. New acquired skills, knowledge, experience are not only improving the quality of service in the general, they also open up new human service opportunities. Under human characteristic, we have preference that correspond to a person's preference for work environments and outcome that could affect service availability such as time, location, price, and so on. Abilities that express innate human attributes. Performance factors, which are internal and external variable aspects of human behavior and the context or environment that can affect human performance reliability. We also have knowledge, skills, experience that are similar to ones in the ONET framework. This picture is showing how our ontology model can enrich IBM's MapK reference architecture, where we use the hierarchical control pattern. We can see two layers of MapK feedback loop is implemented using the SOA paradigm. MapK loops at different levels interact by exchanging information that contributes to new knowledge stored in a shared knowledge base that other hosts can access. The top layer is service broker that carries out service provisioning, composition. The second layer is self-adaptive systems with MapK loops that interact directly with managed resource or subsystems, representing machines and human. Depending on the service flow directions, each self-adaptive system at this layer can be a service provider when delivering service and service consumer when using service. We use a health clinic that uses a web chat as its service channel where the patients can take advantage of the service to ask questions about clinical services, doctor schedules, book a GP, and get health advice. Patient Adam accesses the web chat service to consult about the health problem he is experiencing. For every new session request, the chatbot service by chatbot Kathy is allocated first. Kathy answers Adam's questions, relying on its AI and knowledge from the local and shared knowledge base. During the conversation, Kathy acquires information from the chat with Adam and stores it on a shared knowledge page for others to use. Adam repines of discomfort in his head, yet Kathy's answer don't quite satisfy him. With natural language processing and through its map-k loops, Kathy detects Adam's emotion and upsets. Kathy then sends a service discovery request to the service broker with several criteria. Based on the criteria given by Kathy, service broker discovers and invokes service implementation candidates that meet the invocation criteria. Turns out, the chat doctor service by Dr. David is a suitable candidate. The service broker invokes the chat doctor service for Kathy, which then gives David access to join the chat session. At this point, Kathy becomes a service consumer to David, as well as service provider to Adam. David provides an adaptation service for the chat Kathy to provide a better quality of service in the future. Kathy acquires the knowledge from the conversation between patient Adam and Dr. David. At the end of this story, David gives some advice to Adam and they agree on a schedule for offline meetings. Adam, who was initially upset, ends the session with good satisfaction. Happy ending. We provide a qualitative and quantitative evaluation of our ontological model, referring to Francisek 2009, to ensure our design adheres to certain desirable criteria. Accuracy is a criterion that indicates whether the axioms of ontology comply with the domain knowledge. We have made every effort to make each element or concept expressed in class or relations in this model comply to existing standards and literature. To provide accuracy, we ensure that the axioms should constrain an ontology's potential interpretations such that the resulting models are consistent with the user's conceptualizations. In this picture, we have two axioms generated by protege from our model that consistent with the concepts above. Completeness measures if the domain of interest is appropriately covered. The domain of interest of this model is to promote human-machine service provisioning so that we ensure our ontology is able to answer several basic competency questions, CQ, related to service delivery. As shown in the table, we compare our model with the existing related model, HSCD and PE ontology. Our model provides the answers to given CQs, while the other two models require ontology evolution by changing and developing the new concept into several subclasses of ontology to answer questions related to skills, knowledge, and abilities. Adaptability measures how far the ontology anticipates its use. It should offer the conceptual foundation for a range of anticipated tasks and allow extension, integration, and adaptations. Our proposed ontology enables not only human-machine service provisioning, but also machine-only and human-only service provisioning. However, one can leverage existing concepts in our ontology for other purposes. Clarity measures how effectively the ontology communicates the intended meaning of the defined term. This criterion can be measured by using class relation ratio. We can formalize as the function of ontology O equal to absolute value of CO divided by the absolute value of PO. CO is the cardinality of the set of classes represented by nodes in ontology O, and PO is the cardinality of the set of relations in O. In this table, we compare our ontology model with HSCD and PE ontology. In this illustration, we can see that our model involves more classes and relations than the other two models. We have the lowest CRR, where lower CRR value means our model provides more clarity. Consistency describes that the ontology does not include or allow for any contradictions. We ensure consistency using two different methods. First, we rely on the output of Hermit reasoners that provide efficient reasoning and ontology consistency tests. Second, we use the ontoclean methodology to analyze the taxonomy of classes that have subsumption relation, and our ontology is consistent according to ontoclean. The ultimate vision is to transit the problem of service composition into a collaborative human-machine service composition where bidirectional infosymbiotic cooperation or learning between the machine and human can be envisioned, promising more dependable and human-centric CPS service provision. We propose a conceptual SOA ontology model for human and service provider in CPS. We call this as SOA HITL CPS ontology model. We use a scenario from the medical domain to illustrate how our model can be instantiated. We have reported on how self-adaptive reference architecture models such as MapK can be refined and leverage our proposed model. We follow standard and commonly used approaches to evaluate the ontology against criteria that relates to accuracy, completeness, adaptability, clarity, and consistency. That's all. Thank you very much for your time.